All right, so today we're going to take a look at finding area between two curves. And to start with, I kind of want to draw a visual, a basic idea of how this works. So we're going to consider these two graphs below, the graph of f and then the graph of g. And f is my top graph, the way that I've drawn it, and g is the bottom. To draw a sketch of these, there's absolutely nothing important on this particular slide about units or anything like that. So just draw a curve that sort of looks like a concave down curve on top and a concave up curve on bottom, and places where they cross. And I don't really even care whether they cross above or below the x-axis, but if you want to get it more close to mine, I've got mine crossing both above the x-axis. Okay, so just a swooping curve that crosses like this. This is what you're looking for. See how easy it is to draw? Nothing important at all about how or where. Okay, just draw them in there. All right, so what our goal is to find the area that is trapped between them. So we have these two curves that cross, and we want to find this, I don't know, sort of corncob shape that's between them. And so how can we do that? Well, we actually have some really good tools to be able to do that, and those tools are integration. So if we were to find, let me get these pieces off of here now. If we were wanting to find these two pieces, we would actually be able to take the graph of f that's between where this particular point crosses here and here, and we could find the area from that graph all the way down to the x-axis, couldn't we? We do that with integration, yeah? We just would integrate this thing from whatever this intersection point is. My intersection point happens to look like it's x equals -3, this particular one, and it goes over here to x equals 0.5, right? So from one place to the other place of the graph of f of x dx. And we would find sort of this area that's now in red. Okay? But that's too much. That's not the area that I originally shaded, right? How could I get rid of that extra area? That is the area right here.
By finding the integral of that and the difference between both of them.
Right, so if I were to find the integral now from the function g of x, that would be the area from that blue piece down, wouldn't it? And again, it's the same in limits of integration from -3 to 0.5. And then, like Janet said, I would subtract. I would find the difference between those two areas. And what that would give me is that trapped area that I was interested in finding that was between them. Because I took the top area and I subtracted off that bottom area. Now the cool thing is that this works whether or not the curve is above the x-axis or below the x-axis. And even better is that you guys have antiderivative sort of properties that allow you to combine this in a more simplified form. So in particular, what we can do is we can take the integral and we can subtract the top function minus the bottom function over whatever interval we're looking at, either whether it's places where they cross or simply just locations from one place to the next. If we have the limits of integration as being a, so a is over here and b is over here, then we can find the difference between these two functions and then we can integrate. Or we could find the integral of the two functions and then find the difference. It's the same thing. So this is what we're going to be doing in this section, okay? So like I said, it doesn't really matter whether it's above or below the x-axis. So some of them we deal with will be above and some of them will have sort of a difference between the two things going on. But let's take a look at the first one. So we're going to sketch a graph corresponding to the following integral and then shade the integrated curve, the indicated curve, excuse me. So if you have a calculator with you, now would be the time that you probably would want to use it. If you don't, just look over at the neighbors or look at mine when we get them drawn. These are my two functions, okay? So we're going to sketch a graph based on the original problem that we're given. So the original problem sort of indicates, and I recognize that when we actually integrate this and find this, we'll consolidate that first. But we're starting the problem as it's given, okay? So we are going to put into y1 in your calculator 2 minus x squared, and in y2 in your calculator x squared. Okay, so you're looking at two different curves. All right, so you know what the graph of x squared looks like. That's just the parabola, right? So it looks something, that was not good. Let's try again. Something like this. It should hit the origin, and I didn't quite hit the origin, but Yeah.
Are you putting x squared or negative x squared?
X squared. Because if you take a look back at that formula we had, that negative is a part of the description. We're actually looking at the two of them and subtracting them. So we're just going to put in one of them as x squared. The other one is 2 minus x squared. And my image, I'm expecting, looks something like this. I know my picture's not quite symmetrical and yours is much more so in your calculator, but it does have that basic shape. Does it look like it? Okay. Now, looking at the curve, you actually can also tell, hopefully, if you were to zoom in, the locations where these actually cross, because these are pretty clean ones. Where do these cross? What x values? They're at 1 and -1, aren't they? And that's actually the reason this particular problem has the limits of integration from -1 to 1. Okay, so I'm actually going to be finding trapped area in this problem, the area from the top curve to the bottom curve. And you notice that that top curve is the 2x, is the y1. I'll call it y1 since I put it in as y1. And this bottom curve is y2. Right? I recognize top and bottom switch once they actually intersect each other. But for the portion of the graph I'm looking at from -1 to 1, the top curve is y1 and the bottom curve is y2. Okay, is everybody with me on that? Okay, so this is the first part, which was sketch the graph corresponding to the integral and shade the indicated area. Now, if we were wanting to go further, we aren't asked to on the problem, right? We aren't asked to actually find this area. If we were wanting to go further, what would we do? You'd integrate it. And do you think we might want to simplify it first, Jordan? Sure. I mean, there's no reason to integrate x squared twice, right? We're just going to combine them and then we would integrate. And then we use all the same integration rules that you guys know and love, and this one is a really straightforward one to integrate, yeah? Okay. So again, this one doesn't ask us to integrate, it just asks me to draw it, so this is the only part of this graph, that, or part of the problem that I'm asked to do. Let's try another one. Now, on this one, I am asked to sketch it, just like on the last one, but the second part actually says what? We're going to find the area on these ones, okay? We have two more we're going to do, and we're going to actually find the bounded area. Now, what's different about this one? It's in terms of y, and that's a little bit awkward, isn't it? Because I can't take my calculator and plug in stuff in terms of y. I mean, we can't do that, okay? So what we're going to do is we're going to actually take each one of them and we're going to solve them for x. That's the first thing we're going to do. So this is, solve them for y. This is x equals y squared. And this is x equals y plus 2. So we're going to resolve these problems, and we're going to solve them as y equals. So on the first one, what would I do to solve that for y equals? I would square root. But what happens when you square root? You get a plus or a minus. So this is y equals plus or minus the square root of x. How about the second one? What will y equal? It will be x minus 2. Now you can actually enter those in your calculator. I know it will take 3 y equals because you've got the plus and the minus. So you can do this as y1 is going to be square root of x. You can put y2 in as the negative square root of x, and then you can put your y3 in as the x minus 2. So grab your calculator, take a look. So the last one aside, if I were to just graph those first two together at the same time, what does it look like? Looks like a sideways parabola. So I have an image that looks something like this, right? What does the graph of the other one look like? It is a line. Where does it cross the y-axis? -2. So here's crossing down here at -2. And it crosses further up here somewhere as well, yeah? Now, the curve that or the interest that I have is actually between those two particular points, the points where they cross, because it says find the bounded area. So we actually have to figure out where these two things are crossing in order to do that. You might be able to tell visually on your graph, but occasionally you're not able to tell visually on your graph where things cross. So if that were the case, what would you do if you can't look at that and say, hey, I know they cross at these particular points? What could you do? Yeah, you could set them equal to each other. And in fact, I'm going to go back to the original equations before we solved for x's and all that good stuff and set them equal to each other so you can see that from that perspective. So we're going to take the original equations and we're going to set them equal to each other. So the original equations were y squared and y plus 2. Right? How in the world do you solve an equation like this? Yeah, all on the same side, and then you factor. So I'm going to put them all on the left. I've got y squared minus y minus 2 equals 0. And I'm going to factor. How will this factor? I'll get my y's in there. What's next? Good job, Jordan. Negative 2 and positive 1. So what does y equal? 2 and negative 1. Now, this is negative 1 down here, and this one is positive 2 up here. So for the purposes of drawing, I solved this for y. The problem, I solved this for y. For the purposes of drawing, I got it in terms of x. For the purposes of integrating, I do not want to integrate this with respect to x, and here is why. Notice, this shaded area inside of here, if I integrate with respect to x, what is my top function? What is the graph that's on top? The square root of x. The positive one or the negative one? Well, on the top, it's the positive one, right? The problem is that on this part of the graph right here, while the x squared is on top, the other graph is not always on bottom. Watch what I mean by this. This graph, the line itself, is on bottom until I get to whatever this x value is. But this portion of the graph right here, it isn't. The square root of x that's negative is actually on the bottom part of this graph. So if you were to zoom in other words, oh, that's not good. There is a portion of the graph, that's not drawn right. Here, I'll do it there. There's a portion of the graph, namely this piece right here, where that negative square root of x is the bottom equation, isn't it? Because the line part isn't even in that bounded piece. It's not even there. So this is a problem. I've got a different bottom function for a part of the graph. But if I look at my graph sideways, I don't have that problem. So imagine this graph now, where the top of the graph is the positive x part, and you're going down this direction. So can you look sideways? Can you turn your head sideways and imagine that? If you look at this piece of the graph, if you look at the graph from this perspective, the top graph is always this piece, right? And the bottom graph is always this piece. And this piece that's curved right here, being the bottom part of the graph, has one equation if I leave it written in terms of y's instead of in terms of x's. It has the equation y squared. So I'm looking at it kind of like this. If I were to be finding a sliver of area, I'm looking at it like I have an area, a piece of a rectangle that's going sideways instead of going up and down. Normally we draw our rectangles or we draw our area as though we go from the top down. We're going to go from the right back. Okay? So taking a look at this one, the graph that's actually on top, if I look at it from this perspective, is the line. It's the y plus 2. I think I've got another slide. Good. So I'm actually going to do my integral with y plus 2 as my top graph, and then y squared as my bottom graph. And I'm going to write this in terms of dy, and here's the beauty of this. When I found where these graphs intersected, I found where they intersected in terms of y, didn't I? So I don't have to change this into saying, oh, well, when y equals 2, x equals this, and that's my new limit of integration. I don't need to do that, because these are all in terms of y's. So my lower value in terms of y is negative 1, and my upper value in terms of y is positive 2. So I can set this up sort of as a sideways perspective so that I don't have to deal with the fact that I had 3 equations in order to get the graph. I don't want to deal with 3 equations. I just want the 2 I started with. Does that make sense? The nice thing about this is also I can integrate this easier than I can integrate square roots, can't I? Yeah, I mean, these are easier, they're cleaner to work with. So that's also a nice feature of being able to work with it from this equation instead of from the other equations. I've got 2 equations to work with instead, and I don't have square roots to deal with. All right, so let's integrate. What do I have for my integral on this? Y squared over 2 plus 2y. Perfect. Thank you, Chelsea. And then we're going to evaluate that at 2 and at -1, right? Always evaluate the top number first. So I've got 2 squared over 2 plus 2 times 2 minus 2 cubed over 3. Got all of that minus -1 squared over 2. Hang on, that doesn't look very good. Plus 2 times -1 minus -1 cubed over 3. All right, so what do we get from the first piece? Didn't re-simplify my first set of brackets.
2 plus 4 minus 8.
Okay, 2 plus 4 minus 8/3. So 2 plus 4 is 6. 6 minus 8/3 is what?
10/3.
It is 10/3. Okay. I know some of you are not fond of fractions. You should be, but you're not. So grab your calculator if you want your calculator to show you how fond it is of fractions. How about the next part? Yep, I'd have 1/2 minus 2 and then plus 1/3. So this would be -3/2 plus 1/3, which becomes what? It is -7/6. So I have 10/3 minus 7/6 minus the negative's positive. What's my result? Okay, 27/6. Does it reduce? 9/2. There you go. You can leave it as 9/2, or if 9/2 bothers you and you really want to put it in mixed number form, you could write that as 4.5. That's fine. Any of that. One of those 2 forms at the end, or 4.5 even would be okay. One of those 2 forms at the end is what we're wanting. Any questions on that one? It's a little weird because we have this sort of sideways business going on. But that will often happen when we're given a function in terms of y to start with. So sort of anticipate, oh, it's given me in terms of y. I may need to think of this from the side perspective. The only reason that I turned it into x's, maybe I should reiterate, is because I wanted to be able to use my calculator to draw the graph. That's really the only reason I did it. Okay? You could have done it without that, and you could have graphed it without that, and so forth. But if you want to use your calculator, it has to be terms of x in order to graph. So. All right, let's do another one. This one's super fun because it's got trig in it, right? You guys should enjoy trig. You definitely should. All right, part B. We've got one function that's 2 sine x, the other function that is tangent of x, and the nice thing on this one is that they actually tell us we're going to go from -π3 to π3. Okay? They give us the limits of integration. Now that may mean that it's bounded. In fact, it will, because the directions actually say find the bounded area. But the beauty is they didn't make us find where they actually crossed. So that's a good thing. We've got less to do. But we can use our calculator to draw this graph, and you can even use your calculator to set the window. So a few calculator tips as you're graphing on this one. So let's put the first one in y1 and the second one in y2. After you've done that, I'd like for you to take your window, and I'd like for you to make your window first, put it in trig mode. Okay, so we're not going to deal with the π3, -π3 business first. First, I want you to hit zoom trig. So put this in Y1, put this in Y2. What number is zoom trig? 7. Zoom 7. The reason is because that will make your x-axis into hash marks in terms of pi's, which makes it a little bit more reasonable to look at for these particular functions. Okay? It puts the hash marks that every pi has, I think. Okay, after you've done that, I want you to hit window. And I actually want you to set your window so that it goes from negative pi over 3 to pi over 3. So your x minimum should say negative pi thirds, and your y minimum should, and your x maximum should say positive pi thirds. And I know the calculator will turn it into a decimal immediately when you put it in there as to 1 point something or other. That's fine. Once you've done that, just hit graph.
Does it need to be in a certain mode?
Have it in radian mode. Yes, that's true. I'm sorry, Taylor. Yeah,
Shouldn't
you
have
should
it-
you should have it in
should.
radians.
Okay.
So yes, if you are in degrees, change it into radians. Now you're not going to work in degrees ever in calculus. Okay, so make it in radians. I didn't think about that being an issue. Did everybody's change into radians? Okay. Okay. Redo the zoom trig and then redo the window because I think that might. I'm going to watch Parker so to make sure.
Do you
it doesn't-
hit, do you hit 7 and then enter?
Either way. Okay, that's good. Now do the window from
And then
negative
it
pi
does say
thirds.
this.
Yeah, that's fine.
Okay. Window.
You have to wait for it to stop, yeah. I'll do negative pi over 3 to pi over 3.
And then graph.
Uh-huh. Okay, that's actually showing the same thing it had before. All right, so I'm going to draw mine a little bit exaggerated from what yours are looking like, but I'm going to use Parker's to draw from so that it actually
You're
looks...
gone.
Oh, I am. Okay, well, hang on. Okay, so you've got one graph that looks like this, and you've got another graph that looks like... Oops, let's try that again. This. If you zoom in a little bit, you'll see it gets a little bit more curved, but it does have this curving feature. You actually know where they cross, like we mentioned before. It's at negative pi over 3 to pi over 3. But they actually cross one more time. Where else do they cross? 0, and that's why we're doing this problem is because I want you to see what happens when they actually have two locations where they cross. All right, so here's the tricky thing about what's going on. If I identify what function is on top, it depends on which part of the graph I'm looking at, doesn't it? Yeah. So I don't have them drawn in different colors, and I should have. Let me do that real quick. Let's draw the graph for, let me change my color to something else. I'll try that. My graph for sine is going to be drawn in this green color. Nope, that's tangent, so let's make that tangent then. Okay, so this is my tangent graph. This is g of x, is in green. It'll come up in a second. Okay, so let's start with the left-hand side of the graph. On the left-hand side of the graph, from negative pi over 3 to 0, the graph that's on top is actually the g of x graph, right? And then on the right-hand side of the graph, that g of x graph is actually on the bottom. Agreed? Now, I want to show you two ways to handle this, okay? One way to deal with this is to actually meticulously look at which piece is on top and bottom and to write it as such. So if we were to do that on this one, I'm not going to write sine and tangent in there. I'm just going to write it with the f's and the g's in here. Then I would actually write that on the left-hand side of the graph, I have g of x minus f of x from negative, pi over 3 to 0 and so forth. And then I would add to that the graph from 0 to pi over 3, and I would write in f of x minus g of x. Okay, so this is one way to handle it. This is not my favorite way to handle it because, honestly, I don't really care which one's in top or bottom because I want you to think about what happens. What happens when you, let's just use some numbers, what happens when you subtract 5 minus 3? What do you get?
2.
What happens when you subtract 3 minus 5? You get negative 2. But I contend you still get a 2, right? The only difference is the sign. And if we subtract in the right order, our sign for these areas should end up being positive, right? It should be positive. If we've really subtracted the top one minus the bottom, we should be getting positive areas, okay? So here's what I do instead. It's totally legitimate. I'm not just making this up, okay? But this eliminates me having to care. It's not showing up. We can use absolute values because if I use absolute values, then it doesn't matter which way I subtract, does it? Not at all. Not in the slightest. And so I can still use this idea and I can just put absolute values on the two pieces. I still have to write two separate pieces though. Okay? Okay, so for our functions, what we can do is we can actually, I mean, you can do it in either order. It makes no difference. But we're going to do the integral from negative pi over 3 to 0. And I'm going to do, and you can put the absolute values either inside the integral or outside. It doesn't matter on that part either, because you're just going to take an absolute value at some point. So I'm going to put my absolute values here just because that's where I'm going to put them. And what were my functions? 2 sine x and tangent x. So I'm going to do 2 sine of x minus tangent of x dx. And then I'm going to do my second integral, and it will go from 0 to pi thirds. And it will look exactly the same on the inside, but it is absolutely necessary for me to split these up. Why? You know why? Yeah, it isn't the concavity that's the issue though, actually. Something changes. What changed actually? The top and the bottom changed locations. And because the top and the bottom changed locations, if I don't separate the two, what ends up happening is that one of them ends up being a positive area, and the other one ends up being a negative area, and then I end up with 0. And I shouldn't be ending up with 0, right? So I do need to separate these out so that I actually end up with the two specific areas. In this case, I would end up with 0 because the areas are equal. That's not always the case. You don't end up with always areas that are equal. But you do end up with something that the subtracted instead of added the two areas together, which is unfortunate. So we want to be real careful that we do them in the right way. All right, so we're going to take some integrals. So you're going to have to remember some integrals of sine and tangent. So I bet you remember sine. You may not remember tangent. So if you don't, grab your sheet out so that you can take a look. All right, so we need to know what's the integral of 2 sine of x. It is 2 cosine x, almost. What's missing? The negative. It's negative 2 cosine x. Okay. And then I need the antiderivative, of tangent x. That's the derivative. The derivative is secant squared. What's the antiderivative? The antiderivative of tangent. That's the one. Okay, so the fact that it's negative will change this sign into a positive, right? And it's the natural log of the absolute value of cosine of x. Got lots of absolute values going on in this problem. And then I'm evaluating that from 0, well, at 0 and negative pi thirds. And that's actually the exact same expression that I need one more time, but evaluated at pi over 3 and 0. So plus rather, the integral of this piece, and this one is again the negative 2 cosine of x, plus the natural log of the absolute value of cosine of x. And this one's at pi over 3 and at 0. So all I really need to know is what the cosine is at 0 and at pi thirds and at negative pi thirds. And then I can find all my pieces, right? So let's take a look. Let me get another color. All right, so I'm going to do negative 2 cosine of 0 plus the natural log of the cosine of 0. All that absolute value minus the absolute value of negative 2 cosine of negative pi over 3 plus the natural log of the absolute value of the cosine of negative pi over 3. That is half of the problem. Plus, so let me change colors so that you can identify which piece is which. This is my blue piece. Here's my red piece. Plus negative 2 cosine of pi thirds plus the natural log of the absolute value of cosine of pi thirds. All of that needs to be minus negative 2, yeah, I wrote it right, negative 2 cosine of 0 plus the natural log of the absolute value of the cosine of 0. I'm going to need one more of those and then a parenthesis, I think. Got so many symbols here, I'm not sure. Okay, let's see what we've got. What is cosine of 0? It is, it's 1. Cosine of 0 is 1. So to start with, in blue here, I've got negative 2 times 1, so it's negative 2. So this piece right here is negative 2. Plus the natural log of 1, which is 0, that's right. So we'll come back to that in a minute. These are my absolute values here, my first set of absolute values. Minus, what is the cosine of negative pi thirds? You know? Somebody said it. I think somebody said it. Say it louder, Stephen. It's 1/2. Yeah, it is. It's 1/2. So I have this negative 2 times 1/2. And then plus the natural log of 1/2. Okay, so that's all the part in blue. Red plus, all right, my absolute value, this is negative 2. What's cosine of pi over 3? No, that would be pi over 4. What is it? It's 1/2 again, yeah. Cosine of pi over 3 and cosine of negative pi over 3 are both 1/2. So this is another 1/2. And then I have plus the natural log of, well, like we said, 1/2. And then I've got minus, I opened one, okay. Here's my absolute value. I think I've got an extra parenthesis right here. In which case I've got one there too. Okay. Negative 2, and then cosine of 0 we already established a minute ago was 1, right? Plus the natural log of 1. There we go. I think that's enough different brackets and symbols. Okay, so we established that this is 0 and this is 0. So let's take these pieces out of their absolute values now. So I've got the absolute value of negative 2 here, which is actually 2, minus, over here, I've got negative 2 times 1/2, so that's negative 1, plus natural log of 2. So I've got the absolute value of negative 1 plus the natural log of 1/2. Plus. All right, what's next? Well, I've got the absolute value, well, that's negative 1 again, isn't it? Right here. Negative 1 plus another 1/2, natural log of 1/2. So this looks just like the one I had before, yeah? Oops. Make sure I'm getting what I have written down over here. Oh, I know what's wrong, but I'll fix it here in a second. Okay, and then we have, what's left? Minus 2 again. Okay, here's what's wrong. I've got some absolute value signs that are just misplaced. The absolute value signs need to be around the whole thing. not each div piece. Let me do them. Here we go. That will fix that.
So will that be 2 plus 1?
Yeah. And it'll actually be -2 here then. 2 minus a negative, so that'll be +1. And minus the natural log. And then I've got to remove that one and fix this piece at the end. The unfortunate thing is my absolute value signs are really looking like ones. That one's an absolute value, that one's an absolute value, and that one's an absolute value. And then I had one here and one here. So this is actually +2 here. Did I get them right? Let me double check what I've got written down here. I think so. Yeah, I think all my pieces are okay now. Okay. All right. Here's where I'm working from now. Okay, let's clean up inside each individual absolute value. All right, so this is -2 plus 1, as we said. So this is actually -1 minus natural log of 1/2. Still have these issues with my ones and my absolute values. Plus, and then this is +1 plus the natural log of 1/2. Did I get that right? Okay, so let's think for a moment. I've got -1 minus the natural log of 1/2. So what happens when I take the absolute value of that first piece, the part that's got the red brackets around it right now, the absolute values? What is it? Yeah, it is 1 plus the natural log of 1/2. And I've got absolute values around the 1 plus the natural log of 1/2, so what's going to happen over there? It's to stay the same, right? Now, it looks like what we actually did is just sort of removed absolute values. We actually really didn't. Somebody tell me real quick, what is the natural log of 1/2? Just grab your calculator. It's going to be a decimal part. What does it say? What is the natural log of 1/2? 0.693? Okay. So if I had, is it negative?
Yes.
Negative 0.693? If I have -1 minus a negative 0.693, is that value positive or negative? Is it? If I have, let me write what I said. If I have -1 minus a negative 0.693, that number is negative, which means that to change the sign on it means that I would actually take away that negative. Or I'd multiply everything by a negative, wouldn't I? So when I change the absolute value right there that was in the red to being 1 plus natural log of negative, or of 1/2, what I really did, you didn't see it, but what I really did right here is I said, okay, well I want the negative of the -1 minus the natural log 1/2. I want the opposite of what's in there. That's what absolute values do, right? They actually are the opposite of what they originally were. So the opposite, oh, for Pete's sake. So it's the opposite of what's actually inside of that. That's what absolute values do. Absolute values make things change signs. So changing signs is equivalent to multiplying everything by -1. Okay? Now, the same thing actually happened, and it sort of didn't appear like it did, but it really did, on the second one. That 1 plus natural log 1/2 is actually 1 plus a negative 0.693, wasn't it? And that value is actually positive. And when values are already positive and we've got absolute values around them, all we have to do is lift the absolute value signs off. So it's sort of hidden that that's what we did. It looked like something that wasn't really happening, but this is what we end up getting. And the beauty of it at this point is that if I combine these two, I get 2 plus 2 natural log 1/2, right? Because they are identical pieces.
So this right
yes.
here is the same thing as the 1 plus 1/2.
This is equivalent to this.
Okay. Okay. No,
These two are
if I
equal to each
write
other.
it down.
This piece, well, let me write this way. Now each step is equal to the next one. So this part right here, where I put the extra negative on the outside, came from these pieces. They're all equivalent to each other. Yeah. And it's perfectly fine to leave it written this way. The other thing that you might do, or you might see if you were looking in the back of the book, is they might take that 2 in the front and write it as a power. They might. They probably wouldn't, but just so that you're aware, if you just see it, it might be written like this, or be written as 2 plus the natural log of 1/4, or something like that. There's a couple other options, but what's in brackets is probably the most reasonable place to stop at, but just in case you see something else, you know how to express it. Any questions on that? The part about what we just did on that one that made it awkward was the natural logs. Believe it or not, that's the part that made it awkward. The process itself of doing the absolute values is not awkward at all. It's the part that we did with the natural logs that made it weird. All right.